Now, what's the point of telling you about all these different geometric transformations? Well, if you want to do any kind of shape alteration, say of all the pixels in an image of a face or something like that, then you could always make that shape change out of some combination of rotations, shears, stretches, and inverses. That is, if I first apply one transformation, A1, to a vector R, then that makes some first change. Then if I apply another transformation, A2, to the result of that, then I can perform a composition of the two transformations. What I've done is I've performed first A1 and then A2 to R. Now, maybe this isn't so obvious, so let's slow down and do a concrete example. Let's start out with our basis vectors. So we've got our E1 as being 1, 0, and our E2 as being 0, 1. Now let's take our first transformation, A1, as being a 90-degree anti-clockwise rotation. So we're going to work out what happens if we rotate this by 90 degrees anti-clockwise. So E1 comes down to some transformed E1, let's call it E1 prime, of 0, minus 1. So we can put 0, minus 1 in there. And our E2 rotates down here to be some transformed version of E2, which we'll call, which will then be E2 primed, which will be at 1, 0. So then we've got an overall A1, which describes a 90-degree rotation. Now, then let's take another one, another matrix, which also transforms our original basis vectors, our original E1 and E2. And what we'll say is that that is a, let's say, a mirror, say. So that moves, a vertical mirror moves E1 to E1 prime is going to be minus 1, 0. And it's going to leave E2 where it was, if I just reflect vertically. So my transformation A2 now is going to be minus 1, 0, and it leaves the other one the same, 0, 1. Now, let's ask ourselves what happens if I do A2 to A1. So now I'm going to reflect over the result of doing A1. So E1 prime is actually, when I reflect vertically, going to stay in the same place. And that's going to give me E1, let's say, double prime for doing it twice. And E2 prime is going to reflect over here, and it's going to become E2 double prime is going to be minus 1, 0. So I'm going to have an overall result of doing A2 to A1, which is going to be what I get. E1 prime I first write down, 0, minus 1. And E2 double prime I'm going to write down, minus 1, 0. Now, I can work out what that is actually in a matrix way without having to draw it all out by saying A2 to A1 is doing A2, which is minus 1, 0, 0, 1, to A1's basis vectors. And A1, sorry, A1 there, A1 was 0, minus 1, 1, 0, which is just the two transform basis vectors, the single primes. And when I do that, I just have to do this matrix to that basis vector, and then this matrix to that basis vector. And what that looks like, if I do that, is I do this matrix to that basis vector, so I do that row times that column, and that gives me minus 1 times 0 plus 0 times minus 1, that gives me 0. And that one to that one, so the second row, first column, gives me 0 times 0 plus 1 times minus 1 gives me minus 1. And then I do that A2 transformation to the second column now, to the second basis vector of A1. So minus 1 times 1 plus 0 times 0, and minus 1 times 1, second row, 0 times 1 plus 1 times 0 gives me 0. So I do the row times the column for all the possible row and column combinations. So that is, in fact, the same thing. So we can have discovered really how to do matrix composition or matrix multiplication, doing one matrix to another transformation matrix. Notice that geometrically we can show that A2 then A1 isn't the same as doing the transformations in the other order, first A1 then A2. So just watch that for a minute. So this one we've done A2, and then what if we then do A1? Well, A1 is a 90-degree rotation, so if we rotate E1 prime, then we find that E1 double prime would be equal to our original E2, that is O1, and our E2 primed, which was just staying where it was, when we rotate that down, then that'll come down to here. That'll come down to 1, 0. So our E2 double prime will be 1, 0. Let's look how that works out matrix-wise. So if we do A1 to A2, A1 was 0, 1, minus 1, 0. And if we do that to A2, which was minus 1, 0, 0, 1, then we've got to do that matrix multiplication. And what that's going to give us is 0 times minus 1 plus 1 times 0, 0. Then this one times this one, minus 1 times minus 1 plus 1, 0 times 0 is 1. This row, second column, 0, 0, 1, 1. And second row, second column, minus 1, 0, 0, 1 gives me 0. So that is, the first column is 0, 1, and the second column is 1, 0. So that isn't the same as doing the operations in the other sequence. You see these minus signs are flipped. In effect, what's happened is this composition, rotating and then flipping over, is the equivalent of reflecting the whole lot, the original basis vectors, in this mirror, and flipping and then rotating round. The effect is I've just flipped my original axes, E1 and E2, which is putting a mirror in here. So doing the two operations in opposites in different sequences doesn't give you the same operation. What we've shown is that matrix multiplication isn't commutative. A2, A1 isn't the same as A1, A2. So we have to be very careful with matrix multiplication. We can do them in any order, meaning they're associative. That is, if we do A3 to A2 to A1, we can do A2, A1, and then do A3, or we can do A3, A2 to A1. So we can do that and then that. Those are the same. They're associative. But we can't interchange the order. We can't swap them around. It's not commutative. So this is interesting. There seems to be some deep connection between simultaneous equations, these things called matrices, and the vectors we were talking about in the last module. And it turns out the key to solving simultaneous equation problems is appreciating how vectors are transformed by matrices, which is the heart of linear algebra.